All right, so continuing on from our last lesson where we discussed the properties, some basic properties of exponential functions. And so if you recall from our last lesson, our learning goals were to identify properties of an exponential function and then explain why some of them exist. So things like why their y-intercept is where it is, why they have, in its most basic form, why the asymptote is at y equals 0, whether they are increasing or decreasing. We know that they're increasing when b is greater than 1, decreasing when b is in between 0 and 1. In today's lesson, we're going to continue on. So it's still part of the same lesson. We're going to add on one new property and then look at some word problems that we're going to solve online using Desmos. All right. So we're going to add on another property and then solve online using Desmos. So this time we're going to be looking at, instead of the most basic form y equals b to the x, we're going to be looking at y equals a times b to the x and the effect that a has on the function. All right, so let's go into our lesson and let's begin. So far, just like I said, I've already kind of discussed everything in here. Okay, we know that when b is greater than 1, we're increasing. When b is greater than 1 but greater than 0 but less than 1, then we are decreasing, and that there's an asymptote at y equals 0. But again, I want to stress that that is for the most basic function, f at x equals b to the x. All right, that is what's considered the parent function of exponentials. And then from there, we can have all kinds of transformations. We can shift the graph up, down, left, right. We can vertically stretch or compress it. We can horizontally stretch or compress it. We can reflect it. And kind of the full version of the function would look something like this. F at x equals a times b to the power of k times x minus d plus c. That's a whole lot of letters. We're not going to be dealing with all of those with all of those different properties and transformations. Okay, what we're really going to focus on in this lesson pretty much is, when it comes to the word problems, is we're going to be focusing on y equals a times b to the x. And so, like I said, in previous lesson, we just did y equals b to the x, but now we're adding in one of these transformations, okay, the letter a. And so what I want to do to start is observe what effect the letter a has on a function. So what we'll do is we'll start with the equation y equals 4 to the power of x, or f at x equals 4 to the power of x. And I'm going to add in, so I'm still going to have 4 to the power of x. So my base is still going to be 4, but I'm going to add in a 3 here in front. So my a equals 3. All right. So we're going to see what changes occurred. So let's make up some x values here to sub into my equation, and then we'll figure out the output or the y values that go with it. So let's go with -1, 0, 1, 2. Okay. So I just made those up. Now let's take a look at what our output would be, or our y values, if we subbed in those x values into our function. So 4 to the power of -1. Okay, you can do that in your calculator and you get 0.25. You can also use our exponent law. Since it has a negative exponent, flip it, and you get 1 over 4 to the 1, which is just 1 over 4, which of course we know is also 0.25. Okay, 4 to the power of 0, we know anything to the power of 0 is 1. 4 to the power of 1 is 4. And 4 squared is 16. Okay, so our coordinates here, just so I know what they are, is -1.25. I've got 0, 1, 1, 4, and 2, and 16. So what we're going to do is we're going to graph each scenario, and we're going to see the effect that a had, that value of 3, what effect did it have, right? So let's take a look now, and I'll do a table of this as well now, and then we'll just graph both together. All right, so I'm going to choose the exact same x values so we can really observe the differences. And now I'm going to go 3 times 4 to the power of -1. We know that 4 to the -1 from the previous question is just 0.25, so it's really 3 times 0.25, which is 0.75. 3 times 4 to the 0, which is really just 3 times 1. And then 3 times 4 to the 1 is really just 3 times 4. And then 3 times 4 squared, okay, is 3 times 16, which is 48. Okay, so now let me write out these coordinates so that we have them. Well, let's analyze right now. Before we even graph, let's analyze what's going on here. Like, let's look at these coordinates here, and let's look at these coordinates here. Did the x values change? No, they didn't, right? What changed? It certainly appears as though the y values changed. And can you figure out the pattern of what happened to these y values? Like, how did we go from here? What did we do to go from 0.25 to 0.75? And then from 1 to 3, and then from 4 to 12, and then 16 to 48. I think you probably have noticed that we actually multiplied those y values by 3, which makes sense, right? Because our a value was 3. So we basically just tripled all of our answers. So our x's stayed the same, but our y's were multiplied by 3. All right, they tripled. All right, and so what effect do you think this will have on their graphs? How do you think this will affect this new curve by multiplying all our y values by 3? Yeah, I mean, it's hopefully you're thinking it's going to stretch it out, right? These numbers are getting larger, but the x's are staying the same. The x values are staying the same, but the y's are getting larger, so it's kind of getting stretched out here, right? So let's begin by graphing this. All right, so let's think of a scale. My x's looks like I can just go by ones, right? Because I'm just -1, 0, 1, 2 on both curves. But then I have 0.25, 1, 4, and 16 on the y. And I have to go all the way up to 48 here, right? I've got to go all the way up to 48. So we need to decide what to go by here. I'm going to draw, as best as I can, a straight line here. Okay, I don't have a ruler function here, so it's not going to be the best line there. This is going to be my x-axis. This is my y-axis. Okay, and again, let's just go by -2, -1, 0, and then 1, 2, 3, 4, 5, 6. Not that I need to go up this high, okay? But we can even go really by 0.5s, right? Because look at how many, again, I want to go through this process with you. So I know that my x's only go up to 2, and I'm all the way up to 10. I'm not going to be using much of my graph, right? So maybe we should just go by 0.5s. That might take up more of my grid and might look a little bit nicer. So let's do that instead, okay? So I'll just go -1 there. That'll be -0.5, then 0, then 0.5, then 1. And 1.5, 2. So basically just skip a line, and that means we're going by 0.5s. Okay? Now we've got to go all the way up to 48. So let's decide here what we should go by. Maybe, can we go by 3s? I mean, just go to your grid and try it out. 3, 6, 9, 12, 15, 18, 21, 24. Nope, doesn't look like we can go by 3s. Maybe by 6s might be a little bit better, right? So let's try that. And the reason why I'm going by 3s and 6s and whatnot, I know that 6 will go into 48, 3 will go into 48. And so I'm just trying to use numbers that might work there. We may even be able to go by 4. I know 4 will go into 48 as well. But those are the kind of the numbers that you want to go by potentially. All right, 2 would be ideal, but there's just not enough space for 2. Okay, so let's see here. Let's try 6s. So 6, 12, 18, 24. It's definitely going to be good if we go by 6s. All right, so I'm going to go 6, and then I'll skip a line and say 12, and then 18, 24, 30, 36, 42, and there's your 48, and we'll go a little bit higher, 54, 60. Okay, so that was my process. So don't get frustrated if you're coming up with a scale. It could be a frustrating task, right? So just stick with it, erase it, go back, try a new scale until you get something that works. All right, so let's begin. So we've got -1 and 0.25. So that's basically going to be almost touching your x-axis, right? And we're obviously going to have to ballpark that. 0, 1. Okay, again, we're going to be ballparking where 0, 1 is, slightly higher, right? 1, 4. Okay, again, ballpark it. 2, 16. Okay, 2, if that's 18 there, then 16 will be right underneath it. And you can draw a basic curve, okay? Now let's try, I'll switch pen colors here, and let's try our other graph. We have -1 and 0.75, so just slightly higher, okay? Slightly higher. And we've got 0, 3, so 0, oops. Okay, it's supposed to be in between 0 and 6 there. Doing the best I can. 1, 12. Okay, look what's happening to this graph. And then 2, 48. Okay, so by multiplying it by 3, I have quite the significant change here. Okay, and again, that's pretty sloppy, but it's kind of hard to write on this tablet. Okay, and then this was y equals 4 to the x. Okay, so what changes do we see? Well, for one thing, it certainly looks like it was stretched out. It's being stretched. If I were to grab this curve top and bottom with my hands, it almost looks like I'm just pulling out on it and just making it steeper. So there's no question that it's steeper than the curve of y equals 4 to the x, right? It grows faster. And of course, because the outputs are being multiplied by 3. Okay, so my y values from the original were being multiplied by 3. But one of the significant changes I want to show you that's really, really important is this right here, my y-intercepts. For y equals 4 to the x, what was your y-intercept? It was 0, 1, right? Wherever x was 0. And then you've got y equals 3 times 4 to the x. And where was your y-intercept there? It was different, right? It was actually 0, 3. And if you scroll up, you can see right there, you can see right there that that was our new y-intercept. And there's something to this here. There is a connection between this value and this value right there. Okay? Now, you may not have realized it for this question, or for y equals 4 to the x, you see a 1 there, and you would say to me, but I don't see a 1 in y equals 4 to the power of x. But you actually do, because that equation is actually y equals 1 times 4 to the power of x. So there's your 1, right? And your 3 corresponds with the 3 that's in front of your 4 to the power of x as well. And so that's a common theme, and that is always going to be the case, okay? That your y-intercept will always be your a value. That's basically the conclusion I wanted us to come to here, is that your y-intercept is going to be your a value, all right? And it actually makes perfect sense if that is the case, and I'll show you why, right? So let's say if I were to find the y-intercept of this equation, what value would I need to sub in for 0 in order to find my y-intercept? What value do I put in for 0 as my exponent? 0, right? For every y-intercept, the x value must be 0. And so what happens is anything to the power of 0 just equals 1. And so look at what your y value always ends up being. Okay? So what I want us to conclude from this, okay, is that the a value in y equals a times b to the x stretches or compresses. So in our case, it was a stretch because the value was 3. But if the value was in between 0 and 1, so it was a decimal in between 0 and 1, we would find that it would actually compress our graph. It would make it less steep. Okay, but in this case, our a value was 3. So the a value in y equals a times b to the x stretches or compresses our parent function of y equals b to the x. The a value also represents the y-intercept. Okay, that's important for our upcoming word problem here. Okay, so when we get into word problems that deal with exponential functions, we already discussed from my website there some of the applications. It really has a wide array of applications, from investments to radioactive decay. Multiple different things that apply in the real world uses exponential functions, okay? And in the real world, we have this concept called growth rate and decay rate. Okay, growth obviously meaning that the exponential function is growing, decay rate meaning that it's decreasing. Okay, so for example, you buy a bottle of Advil at the pharmacy, and you notice that there's an expiry date. What that expiry date means is that for every day that the Advil stays unused, there's a decay rate for it, right? And it continuously decays. So whatever medicinal properties are in there decays to the point where when the expiry date comes along, it decays where it may not be functional anymore. So it won't work as well, okay? So that's something that applies in medicine, regardless of the type of medicine. They all have a decay rate, all right? So they decay exponentially. So let's discuss a little bit more detail there. So exponential growth is a pattern of data that shows greater increases with passing time, creating the curve of an exponential function. For example, if a population of mice doubles every year, starting with 2 in the first year, the population would be 4 in the second year, 16 in the third, 32 in the fourth, and so on. The population is growing to the power of 2 each year, so in this case, that would be exponentially. And then decay rate works in the exact same way, just in the opposite direction. So you're decreasing over time, okay, as opposed to increasing. So here is the function for exponential growth. And remember that this is something that we just did, y equals a times b to the x. But now for exponential growth, we see that there's no longer a b value, and instead there's this bracket that says 1 plus r, okay? And then decay instead of b says 1 minus r. So we have to look at why that is, and it's not a hard concept to understand as to why b becomes y1 plus r, okay? Or 1 plus the rate. So r represents rate. So let's say I said to you that population is increasing by 20%, all right? How would you write out that equation as an exponential function? Would you write it, so it's growing by 20%, all right? So would you write it as 0.2 to the power of x if it was growing by 20%? Okay, so this is where you would put your growth, your rate, okay? Would you write it as 0.2 to the power of x? The answer is no, because it's growing by 20%. So it's not, your b value should not be just 0.2. Because it's growing by 20%, it's actually 1 plus 0.2. So it's growing essentially by 120%. So instead of 0.2, you would write 1.2 to the power of x. And so we have to remember to do that. When things are growing by percentages or decaying by percentages, okay, you have to remember that if it's growing, it doesn't make sense to show that it's growing or to have your base value here as 0.2, because that would actually show a decrease, right? It's a decimal. It would actually be getting, your y values would be getting smaller in that case. You want to show growth and you want the y values to be growing. And so what you do is you multiply, or you have your base value as 1.2, all right? And so that's what I go on to explain here, that the growth rate is determined as b equals 1 plus the rate. Decay rate, on the other hand, is b equals 1 minus the rate. Okay, and here is the example that I just went through. So if a bacteria is growing by 20%, for example, you must multiply your previous value by 1.2 in order for it to grow by this amount again, right? So that makes perfect sense. Like, let's say your population is 1,000 people, right? Now if I said to you, what would the 20% increase of that be? If you just did 1,000 times 0.2, right? What would you get? You'd get 200. Okay, so that's fine. So you have 1,000 people, then another 200 people. So you'd have a total of 1,200 people, right? But that's a two-step calculation. That's a two-step calculation. We can actually do this all in one step. We can actually just, instead of multiplying by 0.2 and then adding it back to the original, we can just do 1,000 times 1.2 and we'd get straight to 1,200 people. And this is the concept, right? So you've got to add that 1 to it so that it's growing and so that the number gets bigger, all right? Because if you just multiply by 0.2, the number is going to get smaller. So decay rate is the exact same, except again, it's 1 minus r. All right, so let's look at an actual example that we're going to use Desmos to solve. So sort of a real world application here, okay? Here it is. The depreciation value of a car can be expressed with the equation V at t equals 30,000 times 0.9 to the power of t, okay? So V represents the value of the car. Remember, this is just in function notation. T represents time in years. And the value of the car should just be in dollars, of course. Okay? So, remember, this is just function notation. That's all it is. It's not V times T. Please don't think that that's V times T. It's just simply communicating that the variables that we have in this equation are value and time. Okay? So we're going to graph this on Desmos, and I left instructions here on how to graph in Desmos. First and foremost, you've got to look at your values here, and so let's study this a little bit more closely. So our A value, okay, is what from this equation? 30,000, right? Which means that's going to be your y-intercept. All right, so keep that in mind. That's going to be our y-intercept, 30,000. That's our initial value. Now, our B value is 0.9. Is that decay or growth rate? If it's 0.9, is our function going to be increasing or decreasing if we have a 0.9 there? It's decreasing. Okay, so notice how I'm doing some analyzing before I even start. Okay, so I have a y-intercept at 30,000 and I have a decreasing function, which makes sense because the value of a car is obviously going to decrease as time passes. Okay, so my question is, what is the initial cost of the car? We've already answered that. It is $30,000. How long will it take for the car to depreciate or decrease in value to 20,000? So first and foremost in Desmos, right? And I left some instructions here. Okay, we're dealing with a y-intercept of 30,000. We're going to have to change our scale in Desmos, right? Because Desmos certainly does not by default have a scale that shows 30,000. So we're going to have to change that. So let's go into Desmos, and I'll actually delete my curve so I can show you guys how to do this from scratch. And I will go back and change these numbers as well to their default values. So this is what you get when you open Desmos. I'm going to hit the gear icon in the top right corner. Now, am I going to change my X values? Remember that I'm dealing with years on the X-axis, time, right? So I'm happy showing -1 to 10 years. -1 I know doesn't actually exist in time. Okay, but that's okay. I'll show a little bit of that side of the graph, even though I know that it's not important for me to show negative values here. And I'll go up to 10 years. So that makes sense. But my Y's, I mean, remember my initial value is $30,000. So I'm going to show a little bit on the negative side, even though I don't really need to. I'll go from -5,000, okay, all the way up to, if my initial value is 30,000, I'll go up to something like 40,000. Okay, and there you go. So this way I set up my scale. Now I can graph my function and do y equals, obviously they don't have the letter V here, all right? But just do, it doesn't matter which letters you use here. 30,000 bracket 0.9 close bracket to the power of A, press A to the power of B, X. Okay, and there you go. There's my curve. Okay. So let me just change one thing here. Okay, so there's my curve. And again, there is my y-intercept. It's going through 30,000. That's exactly what I expect to see. So our question is, when will the value of the car depreciate to 20,000? Okay, when will it depreciate to 20,000? Okay, so I'm basically looking for this somewhere around here, where this line kind of at 20,000 will line up with this curve. And so we can get an exact value from this graph. That's the beauty of graphing technology. Here's what you're going to do to solve something like this, is you're actually going to plot y equals 20,000. So you're going to plot a horizontal line. Okay, so y equals 20,000 is a horizontal line. And look at what pops up. It shows you the intersection point. That's the point we want to see. So I kind of manipulated Desmos a little bit. Instead of like eyeballing where 20,000, how many years it would take for the car to depreciate to 20,000, right? I could eyeball that. Yeah, I know it's somewhere just less than 4, but I can get an exact value if I plot the horizontal line y equals 20,000. Okay, my point of intersection is what I'm looking for, and I'm looking for this time value, my x, this first number, 3.848. Okay, and I lost that there. Okay, but let's go back. All right, now I didn't graph it here because I just did my graph in Desmos. Okay, but how long will it take for the car to depreciate to 20,000? So if this, let's answer our questions here. So question A was the initial value of the car is $30,000. Question B says the car will take 3.848 years, approximately, of course. So just under 4 years. If you said just less than 4 years, I would accept that answer. Because, I mean, 3.848 doesn't really mean much in the real world, right? You would just say just less than 3 years. All right. And then, I mean, you could figure out the months, but I'm not too concerned about that. So just say the car will take 3.848 years to depreciate to $20,000. Okay, so let's recap what I did there. I plotted my curve, and then because I was looking for $20,000 there, a y value of 20,000, I created an equation that says y equals 20,000. And that's a straight horizontal line that shows me my point of intersection that I'm looking for. And all you need to do at that point is click on your point of intersection and it will give you your x value that you're looking for. All right? So that's how you do a word problem here. That's how you can solve just a plethora of word problems if you have the equation and then a number in question that you're trying to take from your